Okay, moving into section 3.2, we want to compare the infinite. And so we're going to use that one-to-one correspondence that we revisited in 3.1. And we're going to see what we can do. I got to see a reproduction of the creation of Adam up close and personal, and oh my goodness, I had no idea how much detail Michelangelo, incredible. If you're listening to this in the fall of 22, Sloman Park Mall has a Sistine Chapel exhibit. You might want to go check it out. Yeah, I'm not getting commission or anything, but it's pretty cool. Okay, so we're pairing up collections via one-to-one correspondence. So we talked a little bit about soccer balls and cars, or at symbols and copyrights. But what about our natural numbers, right? Natural numbers are what we know probably easiest. Natural numbers are 1, 2, 3, 4, 5, 6, and so on. The numbers that you naturally use to start counting. Now we know this continues forever, it's infinite. But what if you took out 1? Now, obviously, we've removed 1, but this is still infinite, right? But which one's bigger? How do we know which one's bigger if we can't write down all the numbers in the set? So what we want to do is we want to find a one-to-one correspondence. And moving on to this next page, and you should read these pages as well. We can't just pick the first thing that comes to mind and say, oh, it doesn't work, right? You might have to adjust your numbering a little bit, right? Things shift. So infinity minus 1 is still infinity. This is definitely the Ted Theodore Logan section. All right, I'm going to do this repeatedly. We're a set of numbers. I'm going to add some. I'm going to take some away, and they're all going to be the same size for the most part. All right, if you're from the United States, you might know that the 50 states that we currently have are related as no one-to-one correspondence with the 50 stars on the flag, right? So we could draw a one-to-one correspondence. We say that these have the same cardinality because they have the same number of things. Okay, so it's a sameness in the number of things. So we might say that the natural numbers, there are as many natural numbers as there are natural numbers without 1. Super weird. All right, let's get weirder. So you have this infinite stack of ping pong balls, and you have this barrel that can hold an infinite amount of ping pong balls. All right, so here's what we're gonna do. We got 60 seconds on the watch. 60 seconds. Here's our timer. We hit start in half that time. So we stop at 30. The ping pong balls numbered 1 through 10 are in the barrel. Oh, bad barrel. And then we take out number 1. Alright, so now we have 30 seconds remaining. And in half the time, at 15 seconds, we pour in 11 through 20 into the barrel. And we take out number 2, because it's task 2. Right? And we keep doing this. We keep cutting the time. Alright, now I have 15 minutes, in 7.5 minutes, and then in 3.75 minutes, and we keep cutting that in half and cutting that in half. And notice that this could be cut in half infinitely. Alright, 1/2 repeatedly. And each time, with each step, we're taking out that number, right? We're taking out that number of ball, but we're adding in 10, but we're only taking out 1. So at the end of the time, how many balls are in the barrel? Right, we poured in 10 at a time. We got these ping pong balls everywhere. A nice little barrel shape here. Which balls are still in the barrel? Well, since this can be cut in half forever, I had tasks that went forever, And I can tell you exactly which ball was removed at step 738. It's ball number 738. And since I could keep on cutting this time in half, I have time to grab every ball out of there, even though I'm adding 10 times as many along the way. I'm telling you, it's the mind-blowing section. Just go with it for now, okay? Now, what if we go bigger, right? Natural numbers, no big deal. What if we add positive and negative natural numbers along with zero, right? These are called the integers. Well, we can still match them up. We can still count. Using the natural numbers, we can list every single integer. The natural numbers and the integers have the same number of items, right? They're the same size, they're the same cardinality, because we have a one-to-one correspondence. So let's make it bigger, right? Let's not just use integers, let's throw fractions in there. Well, if we use fractions, there's no way that could be the same as the natural numbers, right? There's way too many. Well, it depends on how you set up your correspondence. We could use a rectangular grid system, where the numerator is the movement right, and the denominator is the movement up or down, right? Right or left, up or down. And in this, we can define our first step, our second step, our third step, our fourth step, and so on. Wow, did I really screw that up already? I did. That's 4 right there. We could keep going, right? And look at that. We could count every single stop along the way. This -2 over -2, that's the same as -1 over -1. So we never need to hit the rest of these because we already have that number. So every rational number will appear here. You can pick any rational number you want. All right? 2 over 2, we already have that. That's the same as 1 over 1. So we don't need any of these along that line. And we can keep doing that so that our fractions, we only hit the reduced ones even. And that's pretty cool. So we have a one-to-one correspondence. So all of the rational numbers, that's all natural numbers, a positive and negative counting numbers, plus 0, plus all the fractions involving those. That's crazy. Absolutely crazy. So let it be. Just accept it. Let your mind go loose for a little bit. Let it just think about the really massiveness of infinity. Okay, so we can denote the natural numbers symbolically. We're going to use this notation. So the set of natural numbers less than 10. Natural numbers start at 1, naturally. Oops, that's where 5 goes. 6, 7, 8, 9, less than 10, we do not include 10. The set of all even natural numbers, that's 2, 4, 6, that's a 4, I promise. 8, am I going to list all those out? No, we use that dot notation, or ellipses, dot notation to say the rest of them. The set of solutions to the equation x squared minus 4 equals 0. In order to solve that, let me change colors so I don't get too bad here. Let's go some minor orange here. X squared minus 4 equals 0. I hate my 4's here. X squared equals 4. So x equals plus or minus 2. Alright, so that's what our answer would be, is just the set involving -2 and +2. The reciprocals of all the natural numbers. Well, the reciprocals is, flip it upside down. Natural numbers are naturally written with a fraction that has a denominator of 1. Etc. So we could do that. When we flip it, the reciprocal would be now the 1 is in the numerator and the natural numbers are in the denominator. There we go. Alright. Now these problems, if you just let your mind relax, right? Don't overthink it. Just let it be. Remember, you will need more words than the hints that I'm giving you. But if we let n stand for the set of all natural numbers, then we could write 6n for the set of natural numbers all multiplied by 6. So 6, 12, 18, 24, and so on. Show that the sets n and 6n have the same cardinality by describing an explicit one-to-one relationship. It tells you exactly what it is, right? That's the relationship. Don't overthink it. Let C stand for the set of all natural numbers that are perfect cubes. Show that the set C and the set of all natural numbers have the same cardinality. I'm going to take it back to blue. Check out what we could do here. There we go. 1 goes to 1, 2 goes to 8, 3 goes to 27, 4 goes to 64, and in general, the natural number goes to its cube, right? The natural, that's not equal to, don't use equal. The natural number goes to its cube. Suppose R is the set defined by 1 over 1, 1 over 2, 1 over 3. Oh, we're not doing that problem. Moving on. Hotel cardinality. Okay. It is the stranded traveler's fantasy. The hotel cardinality is a full-service luxury hotel with bar and restaurant. It has as many rooms as there are natural numbers. The room numbers start at 1 and go on. You can see why stranded travelers love the hotel cardinality. There appears to be no need for the sad sign, no vacancy. Suppose, however, that every room is occupied. Now it appears that the night manager must flash the no vacancy sign. But you show up. What the heck? Well, we have room 1, room 2, room 3, right, and a hallway. All these rooms. And they're all full. But we could ask everyone politely to move to the next room. We might say indeed that 1 is going to go to 2, 2 will go to 3, 3 will move to room 4, and look at that. Now room 1 is open for the new traveler. And it doesn't matter how many travelers you get. You can always have people move down to the next room because there's always a next room. You can't put somebody in the, quote, last room, but you can put them in the first room, right? So here we are, given the scenario Mindscape 16, the one we just talked about. The Infinite Life Insurance Company has lots of employees, as many as there are natural numbers, and everybody gets a private room. But the hotel's already full. But can we add an infinity into our infinity without kicking anybody out? Absolutely, right? Absolutely. We could have, we would map it just like we would the integers, which we saw earlier in the work there. Sorry, I was trying to think about how to draw that as a hint, but I'm just going to send you back up to where they talk about the integers. Right, that's my hint for that one. Yeah, and the night manager said, screw this, I'm out. Alright, not really. You have infinitely many piles of peanuts. In the first pile, you have 1 peanut. In the second pile, you have 2 peanuts. In the third pile, you have 3 peanuts, and so on. Yep, they don't look like peanuts to me either. How many nuts do you have? You have infinitely many, right? And in the first, yeah, are we adding these up? How many nuts do you have? So I want all total. So I'm asking for 1 plus 2 plus 3 plus 4 and so on. Is this the same as the cardinality of the set of the natural numbers? If not, explain why. If so, provide a one-to-one correspondence. Awesome sauce. I'm going to leave that one for you to look at. I am going to, not finite city, has avenues running north and south. Avenues running north and south, and streets running east and west. And there is a stoplight at each and every one of these intersections. There's a stoplight at each and every intersection. Does the set of how many traffic lights are there? Right, there's infinitely many. Does the set of all traffic lights have the same cardinality as the set of natural numbers? Uh, this is where you will want to look at our discussion on the real numbers. That's your hint on number 32. And number 36, a ping pong balls on parade. This is still major woe territory. I want you to think about it. This time, we're doing 1 through 10, removing number 1. In task 2, we put in the next 100, so 11 through 110. And then we remove ball number 2. And then we put in 1,000 balls and remove ball number 3. We keep doing this for 60 seconds, always half the time, always 10 times as many ping pong balls. And at the end of the time, still no balls in the barrel. It's weird, man. It's weird. It's infinity.